Welcome to the 10th week of your online organic chemistry lab. This week we'll be going over the reaction of cyclohexanol to cyclohexene via elimination, and the elimination in question will be an E1 reaction. The mechanism in question for this reaction is pretty straightforward. We'll just go over some real basics here. Like I said, this is going to be cyclohexanol to cyclohexene, so a cyclic alcohol to a cyclic double bond with the double bond inside of the cyclohexene. Like we said earlier, this is an E1 reaction, unimolecular elimination reaction. So we're going to be eliminating something instead of substituting like the SN1 we covered earlier. The first steps of this reaction is very similar to the SN1 we covered, which was terbutyl alcohol to terbutyl chloride. In both of these reactions, the hydroxyl group gets protonated by either an acid or water or whatever we're using. Water then gets removed as a leaving group because water is a good leaving group, and then you form a carbocation. In the reaction last time, we formed a tertiary carbocation, which was very stable. In this reaction, we're forming a secondary carbocation because anytime you work with a cyclic molecule, all of the carbons in the cyclic molecule are going to be secondary. Unless it's substituted, but in this case it's just a single cyclohexane ring, so they're all secondary. So the question I pose to you is, you have to find on your own, and we will definitely be asked about in one of the quizzes, is if the terbutyl alcohol underwent an SN1 reaction, why doesn't cyclohexanol undergo the same reaction? So just a basic overview here. Again, this is an E1 reaction. It's going to be an acid catalyzed E1 elimination. We're going to be using, generally use sulfuric acid and some heat, which is pretty standard, straightforward. So you start with your cyclohexanol. The acid catalyst will protonate the hydroxyl group. Water will leave. And then what actually happens is the original carbon that the hydroxyl group is attached to, we're going to call that the alpha carbon. Carbons that are directly adjacent to an alpha carbon are called beta carbons. Pretty simple, straightforward. Anytime you're doing an E1 elimination, when you protonate and the leaving group leaves, you form that carbocation, and a hydrogen from one of the beta carbons is basically going to be removed. Will reprotonate water to form acid. That's why it's acid catalyzed. You constantly are going to regenerate your acid. And those electrons associated with that hydrogen will then form a double bond between where the hydrogen left and where your carbocation is. So you'll be producing a cyclohexene molecule and water in this reaction. A little bit more over the specifics of elimination reactions. As I briefly touched on the previous slide, you need to be aware of alpha and beta carbons. The alpha carbon is always where the leaving group comes off of, and your beta carbons are where the carbons are directly adjacent to where your leaving group alpha carbon was. And these are elimination reactions are very, very important because they're one of the more efficient and the main ways to prepare alkenes or carbon-carbon double bond molecules. Anytime you talk about elimination, it's called elimination because there's always going to be some small molecule removed during the process. Could be water, could be carbon dioxide, something along those lines. And generally, when you do elimination reactions, you're going to be forming a double or sometimes even triple bond. So that's a key thing to look out for. Also, you might see this called a 1,2 or beta elimination. All that means is, it's an elimination from the adjacent carbons. And anytime you do an elimination reaction, you're going to form a pi bond. Like I said, it could either be an alkene or an alkyne, a double or triple bond. But in this circumstance, you start out with the carbon-carbon single bond in your cyclohexanols. That's an sp3 hybridized bond. And then when you do a E1 elimination reaction, you're going to form a double bond. And when you have a carbon-carbon double bond, in a case like this, you're going to have an sp2 for the alkene. And if you were to form another elimination, if that would be possible, you would form a triple bond, which is a alkyne, and that is an sp hybridized. That's a real quick way to kind of just memorize it. Is if you have a carbon-carbon single bond, it's sp3, sp2 for carbon-carbon double, and sp3, and sorry, just normal sp for a carbon-carbon triple bond. Here you can notice the exact elimination molecule we'll be talking about. We brushed on it earlier, but of course it's going to be water because your hydroxyl is going to be transformed to water as it's protonated by the acid, and that'll form a leaving group. And then the hydrogen will then reprotonate to regenerate the acid. So you'll be knocking water off of the molecule, and you'll be left with your initial substrate that has been changed to a cyclohexene. This is an E1, just like your SN1. It's a first order reaction. It only matters, the rate of the reaction only is determined by the substrate itself, nothing else. And so it doesn't matter how much acid you have, doesn't matter solvent, temperature, anything like that. It only matters on the concentration of your substrate, or your cyclohexyl in this case. So like I said, it's independent of the nucleophile. It's independent of anything else. And it's just a unimolecular reaction, and it's acid catalyzed because we'll be using sulfuric acid, and it regenerates throughout the reaction. Let's go over the 3 basic steps of this reaction mechanistically. So for step 1, we have acid protonation of the hydroxyl group. That hydroxyl group becomes a oxonium ion, or basically just water bonded to the cyclohexane group, and water has a positive charge. The oxonium has a positive charge in the oxygen. That's not favored. So water becomes a very good leaving group. So that's going to drop off on its own. And when that does drop off, you end up going to step 2. And step 2 shows that water leaving, and in its place becomes the secondary, in this case, carbocation. And your water has fully fallen off, and that's your elimination. You've eliminated water at that point. And then in step 3, the secondary carbocation, now we get to the part of the alpha-beta elimination, or 1,2 elimination, where you can notice the 2 adjacent carbons to that carbocation. Those are your beta carbons, and those beta hydrogens are what are going to be abstracted by water. It could work at either or. It doesn't matter, because if you flip the molecule, it's exactly the same symmetrically. So it's just either one of the beta carbons. And when that hydrogen is abstracted, the electrons associated with the hydrogen are going to form a double bond between where the hydrogen was and the carbocation. And that extra hydrogen that leaves regenerates your acid. And that it will end the reaction, forming your cyclohexene at the end. All right, that's pretty much all we need to cover about mechanisms or any theory beforehand. So we'll move on to the actual procedure of the lab if you were in our actual lab. There are some modifications for those of you that have your textbooks, so be sure to use these slides as your reference if you get any questions on quizzes or something like that. So the first thing you're going to be doing is clamping a 25 milliliter round bottom flask in a ring stand and a hood. We're going to be setting up a fairly, convoluted glassware system, so there's going to be a lot of little pieces to it. You're going to place in that round bottom flask, you're going to place 5 milliliters of water, and then you're going to add 4 milliliters of concentrated sulfuric acid. Concentrated sulfuric is one of the worst ones to work with. It's a very corrosive molecule. It is exceptionally it prevalently oxidizes organic materials, meaning your skin. So it's very, very bad stuff. It fumes. It's because it's concentrated. It's actually it's a lot like kind of like a runny syrup concentration. It's bad stuff. So gotta watch anytime you work with that. Watch that out carefully, and also anytime you're diluting acids or adding acids to a solution, you always add the acid to your water, never the other way around. The chemical environment, when that acid hits that water, it deprotonates and it's highly exothermic. So if you add water to acid, you get a very, very super concentrated area of superheated water surrounded by acid. And you instantly basically flash boil it and cause it to splash, creating gas and a lot of bad problems. So kind of stay away from that. So you always add your acid to your water, so you have that full volume of water to dissipate that heat, and so the whole thing doesn't flash boil. Same thing with bases. Always add base to water too. Always add to the water. Once that's in there, you're going to take the flask, and swirl it, make sure it's fully mixed, and then of course to do that it's easier to unclamp it. So you unclamp it, swirl it around, and reclamp it back in the ring stand. Like I said, it's concentrated strong acid, so it does get hot. So what you're going to do is you're going to cool the mixture back down to room temperature. Don't do anything while it's still hot, because you'll actually see condensation of water, and it might even boil a little bit. Because remember, it's basically it's half and half almost of water and concentrated acid, so it's pretty rough stuff. So once that's cooled back down to room temperature, you're going to add 3.2 milliliters of cyclohexanol, which is equivalent to 3 grams based on its density. You can slowly add that to the above mixture, and swirling occasionally just to make sure it's fully mixed. And you'll add a couple boiling chips to the flask. They're tiny little silicate boiling chips that allow better nucleation of gas bubbles, let the boiling occur easier, and it doesn't bump the liquid inside. It doesn't pop and splash everywhere. So once that's all done, you're going to assemble a distillation apparatus. There's a picture of it on the next slide. Inside your book, there's a picture as well. It's page 331. But that's not a correct thing. It's figure 510, I believe it is. Yeah, 510. And that's not the correct distillation assembly we need for this. So you should use this next slide as your reference for our setup. Here's the correct distillation assembly. We're going to be using an azeotropic distillation assembly, mainly because it's azeotropic, meaning we have basically a solution that has two chemicals that don't mix. We have an organic compound and water, and of course acid will be water-based, and they don't fully mix, but when you start adding heat in certain situations, you always get a combination where both of those molecules kind of interact enough. And when you start to distill and evaporate or boil off these molecules, you'll actually get both of them coming off at the same time. And when both of the molecules are in gas form leaving solution at the same time, that's called an azeotrope. So what we have to do is we can't just boil it and distill it, because you're going to get your water out of it as well as a little bit of cyclohexanol or cyclohexene. We don't want that. So basically we have two different setups and two different traps for the gas. If you notice for the round bottom flask, the bottom left, there's going to be heating mantle under that, and as it starts to evaporate, it goes up in the little Kleisen adapter. That's the little kind of Y-looking adapter there that's stopped. The initial vertical tube is stoppered, forcing the vapor to go up that tube, and that tiny little amount of room temperature cooled glassware is enough to allow your heavier materials to condense back out and fall back into the round bottom flask to reflux and be boiled again, while the lighter vapor is going to continue up the tube into the distillation head where the thermometer is located, and then that's going to be pushed down into the West condenser where you're going to have water flowing. Of course, in this case, you always want water in at the lowest point and coming out at the top, because you want to force water through, always have water flowing to the system. You want the whole thing to be cooled. And then at the very end, there's going to be a small adapter, and the liquid that's distilling is going to condense and drip out into a collection test tube, which you will have encased in ice to have it super cooled at the very end. All right, continue on with the procedure. After everything's set up correctly and adding the boiling chips, you can start heating the round bottom flask's contents gently. You don't want to crank it up too much, because your cyclohexanols and cyclohexenes are rather volatile, and they can boil off pretty quick. So you're just slowly going to continue heating the flask until basically all of the contents of the flask have evaporated off, and you're going to have a little black residue at the bottom of the flask, and you're going to start seeing some fumes. At this point, the distillate you've collected is going to be from anywhere from 2 to 3 milliliters, and it's going to be cooled in the ice tube. And there's going to be 2 layers, because I said it's an azeotrope, so we are going to get a water layer and we are going to get an organic layer. If you look up the densities of these two, the cyclohexene, which is our product at the end, is lighter than water, so it should be floating on top of the water. So your upper layer is going to be cyclohexene, and the lower layer is going to be water. Depending on how well things are mixed or how the reaction goes, you might have a little bit more water, a little bit more cyclohexene that you don't really know. Most likely you're going to have more water because we have a lot of water in our solution and not as much. You only had 3 grams or less than 4 milliliters of the cyclohexanol versus 4 plus whatever was in the acid. So there's going to be 5 plus whatever's in the acid. So there's a lot more water. So what you're going to do is once you have this distillate and you're not getting any more liquid boil off once you get down to those black residue and just vapor, you can turn the heat off and drop the heating mantle. Remember, heating mantles always need to be clamped so you can drop them so it can cool the contents quickly if needed. But you drop the heating mantle, take the heat away, and then you can take that test tube with those 2 layers, and you're going to use a pass your pipette, and you're going to remove that lower aqueous layer. We want to get as much of that off as possible, but try not to remove any of that top layer. So you just submerge it in the test tube at the very bottom and slowly pipette out that water layer. So hopefully all you'll have left is a cyclohexene layer at the top. Now, even though you're only going to have a cyclohexene layer, hopefully, there's still going to be some water around the molecules. There's still going to be some acids in there, so we need to neutralize that. So to that leftover cyclohexene layer, after you've pipetted that water out, we're going to add 1 milliliter of a previously prepared 10% sodium carbonate solution. And this is to neutralize any traces of acids. Because you're working with carbonate or bicarbonate, anytime you work with that in the presence of acid, you're going to form carbonic acid and you're going to form carbon dioxide. So there's going to be foaming. It can be quite reactive depending on how much acid you have or the strength of the acid. And since we're working with concentrated sulfuric, there might be quite a bit of foaming. And you're working with a test tube, so it can easily foam out of the top of the test tube. So you always have to be careful with that, just slowly adding it, make sure it's pointed away from everything else, stuff like that. Once you've added that and it stops foaming, you're going to use a pipette squirting technique to wash the cyclohexene fully with that carbonate solution. Because remember, this is water, plus it has sodium carbonate in it, so it's actually denser than water, so it's definitely going to be on the bottom and cyclohexene will be on the top. So basically submerge a new pipette and you draw up a amount of the sodium carbonate in the pipette and you squirt it through that top layer, and you keep doing that over and over again, basically forcing those 2 layers together without fully mixing them. And that just basically rushes the sodium carbonate through the cyclohexane layer since they don't mix, neutralizing as much of that acid as possible. So you need to do that. We're not working with a whole lot of volume, so you need to probably do that for about a minute just to make sure everything's nice and mixed, and then let the 2 solutions fully separate back into the 2 layers again. And then you're going to remove that bottom aqueous sodium carbonate solution again, like you did with the initial water. Once that's done, you're going to add 1 milliliter of tap water, and that's to wash it again, and that's to remove any excess sodium carbonate that might be attached to your molecules or floating around in that organic layer. Same thing, pipetting action to make sure both the layers are mixed, squirting in and out of each other. Then let it settle after about a minute, and then remove the bottom water layer again. Now we've washed multiple times with water. We created water in the reaction, so there's still, even though we've removed water 3 times, there's still going to be a decent amount of water in your cyclohexanol layer that's kind of trapped there, and some of the excess that you might not have fully gotten out with the pipette. So at this point, we're going to use half a gram of anhydrous calcium chloride, which is basically a deliquescent. It pulls water out of solution. Just a few grains of it is going to be half a gram. It's not very much. You just put that at the bottom of your test tube, you swirl it, and it's going to clump up a little bit. And you're going to have to swirl it quite a bit just to make sure it gets fully immersed in the whole solution and pulls the water out of everything. But after 20 minutes, you'll have more than enough water pulled, hopefully all of the water pulled out of your solution, so then we can move on. Now, this is an optional point, and most likely during the lab we wouldn't have you do this, but if you notice that there's still a lot of water in your solution and you're still getting layers even after all these procedures to get the water out, you might have to do what's called a short path distillation setup. It's called short path because it's very short. We'll get a drawing of the setup here in just a second. But basically, you would transfer that dry cyclohexene to another small round bottom flask. Of course, you would not transfer the calcium chloride because we don't want the solid in there. We just want the liquid 100%. And one of the issues why we really wouldn't do this in the lab is because cyclohexene is flammable, and if you distill it all the way out to full dryness, you could cause flames, explosions, heat vapor, and crack the flask. So we don't do that. But if we were to do it, the next slide will show how to specifically set it up. You might get a question on what short path distillation is versus a normal distillation. So the next slide will show you the setup. All right, here's a very crudely drawn short path distillation setup. Uses a round bottom flask and a heating well just like before, with boiling chips always. And then from that initial setup where we use that Kleisen adapter, the little Y tube thing, you can use, that's what you're going to use for your distillation. And you use short path when you're working with very, very small amounts of liquid, and liquid that's fairly volatile, more volatile than water, so much of organic compounds. So it's the same setup, basic thermometer with the stopper on the top. You leave the Y end of the Kleisen adapter open to the air, and you just start heating it. And since we know we're looking for cyclohexene, you're going to be collecting any of the material that boils off at between 77 and 83 in that range. Upper 70s, low 80s, and then you would extract that with a pipette. And the key thing, like I said, it's volatile, it is flammable, so you don't want to fully distill it all off. You always want to leave the bottom of that flask a little bit wet, so you're not going to fully get all of your material out. So that's, like I said, it's a flammability issue, so we probably wouldn't do it in the actual lab. All right, once all the procedure's done and you have your dried cyclohexene, we're going to then test it for unsaturation. Unsaturation is basically just you have a double or triple bond on a molecule. As a saturated molecule, saturated organic molecule, all of the carbons are fully saturated with hydrogens. So we're looking for unsaturation. There's a couple specific, really easy, chemical tests. We don't have to do any instrumentation for this. The first test you would do is a potassium permanganate test. Potassium permanganate is KMnO3, very strong oxidizer. And it's a deep, deep purple, like almost black. It's so purple. So when you add potassium permanganate to a unsaturated system, you form manganese dioxide, MnO2, which turns brown, and you will hydroxylate a double bond across a double bond, a cis across a double bond. So the cyclohexene in the presence of potassium permanganate will form a brown manganese dioxide precipitate, and then it'll form the compound cis-1,2-dihydroxycyclohexene. That's hard to say. So basically what happens is the two carbons that are associated by the double bond, the two sp2 carbons, you basically are adding a hydroxyl group to each one of those. And it's a cis addition. So depending on how dilute the solution is, you might still have a purple color, but what you're looking for is any change in color from that deep dark purple to a lighter or browner or ruddier color. That'll show that there's unsaturation in there. We're also going to be doing a bromine test, bromine inside of carbon tetrachloride, basically to reduce this reactivity. Bromine's bad, very reactivity. But bromine by itself in carbon tetrachloride is a kind of a reddish orange color. If that starts to go away, you have unsaturation. It will become almost clear. So cyclohexene in the presence of this bromine, you get a racemic mixture of 1,2-dibromo. The bromine adds across the double bond. Racemic meaning you'll get the two possible versions, a syn or anti addition across the double bond, where the bromine's on the same side or the opposite sides. So you'll get a not equivalent, equal, but you'll get a mixture of both of them. But that's what you would be looking for in that specific test. Here's just another slide showing the overview of these tests again. Top section just shows your main reaction of cyclohexanol. They show phosphoric acid, which you can use as strong acid, but we use just sulfuric as plenty for us with a little bit of heat. So when you're doing these chemical tests, you also might see those called qualitative tests, because you're not getting, it's not quantitative, you're not getting an actual result of how much there is, or how many molecules in comparison to what you have. You're just looking to see for a color change. So it did or it didn't kind of type of thing. That's what your qualitative tests are going to be. So the first test shown is the bromine in carbon tetrachloride. That solution is red, And if it is unsaturated, if you do have that double triple bond, you'll form the dibromo compound, which is colorless. So that's that top picture there. You see that bottom solution is completely devoid of color, meaning it was saturated. On the bottom picture, we have the potassium permanganate added to a cyclohexene. And at this point, you get a dihydroxyl cyclohexane, and you form manganese dioxide. It's kind of hard to see in this, mainly because that specific picture still has the calcium chloride at the bottom, so it's going to pull out the water in that calcium chloride. But there is a slight, very, very slight brown tint. But the key thing to look at is the initial test tube is that deep purple. It's kind of dilute, but it is that purple, and it goes away. So that color change is basically what you're looking for. If you had more volume and a higher amount of your compound of question that was unsaturated, you would definitely see a floating brown precipitate in that solution. Okay, some safety issues to talk about for this lab that you might be asked about. Like I said, we were with concentrated sulfuric for this, so very, very bad stuff. You got to handle it carefully. Anytime you're working with any acid, much less a concentrated strong acid, you always add acid to the water. Severe chemical burns, even a drop of this will cause a very, very bad chemical burn. I know from personal experience. If it does happen to get on you, you immediately go to the wash stations and wash that area nonstop for 15 minutes, just nonstop, just deluge the area, get it completely soaked. If you do get it on your clothing, the best thing to do is just instantly remove the clothing, and it's going to. Both clothing is either synthetic or a natural blend of hydrocarbons, and it's just going to chew through those. It's going to turn them black. So you need to take that off as quickly as possible, and then wash the area under the clothing. Also, with this reaction, it's got a chance to produce sulfur trioxide, which is very volatile, and in the presence of air, with any bit of water in the air, it sticks to clothing and forms even more sulfuric acid. So it's just bad all around. So anytime you work with sulfuric, much less concentrated sulfuric, you always have to be careful. Use fume hoods. Be very careful with it. Like we said before, cyclohexane is flammable. It's volatile. That's why we didn't. If we did distill it again in the short pass system, we would never distill it to dryness. There's always fire hazards. Bromine itself is incredibly dangerous. Bromine is it's highly reactive, severe chemical burns, causes eye and sinus damage. If you inhale the vapors, it's very, very volatile, puts off a lot of vapors. That's why we keep it in the carbon tetrachloride. It stops the vapors from coming out, makes it easier to use. Anytime you use bromine in a teaching lab, the TA is going to be the one that handles it, makes the solution. There will always be the TA near the solution in the fume hood when you would be dispensing it. It's bad stuff, and you never take it out of the hood. When you're transferring it from the fume hood to your fume hood, the chemical dispensing to your specific fume hood in the lab, it would always be covered with a wash glass, and walk very carefully. Let everyone know as you're walking around them that you're coming through, that type of situation. It's bad stuff. Actually, it's sulfuric acid is bad. It'll burn you. It'll cause scars. Bad stuff. But bromine will kill you. So that's the difference between those two. Bromine is very, very bad. Because like you said, the point of this is we did the saturation test. So if bromine adds across double bonds and breaks those double bonds apart, your DNA and all your molecules, your phospholipids, everything inside your cells, there's double bonds everywhere. So bromine basically just lyses all your cells, just instantaneously. It just breaks down all those double bonds, unravels everything. It's bad, bad stuff. We also use potassium permanganate. While itself, it isn't anywhere near as bad as any of these other chemicals. It is a very strong oxidizing agent. Anytime you have a lot of oxygen on a molecule, and for instance, in this case, that the manganese atom is highly electropositive. It's got an oxidation state of +7 in the case. Anytime you have that difference of a huge, highly positive molecule with lots of oxygens, that's generally the designation of a good oxidizing agent. So it can cause chemical burns. Nowhere near as much as an acid or anything. It'll cause a slight burn irritation. But the big thing is it will discolor your skin, and that discoloration will not go away until you slough off your skin cells that were discolored. It's a near permanent until that stuff falls off. So You just always got to be careful with that when you're working with it, mainly from the dyeing and the skin discoloration. All right, so once all of that is done and you did your tests and everything, you would weigh your sample and determine, based on its density, because it's cyclohexene, so you could figure out your final. You get a final volume, and then you would change it via the density calculation to a gram amount, so you would know your amount, and you would determine a percent yield. That's just a 1-to-1 reaction. For every 1 mole of cyclohexanol, you should get 1 mole of cyclohexene and 1 mole of water. So nice and simple, just simple mole calculation. If you did the short pass distillation, you would have a temperature range for that. Hopefully it's in that between 77 and 83, but as I said, we probably would not have done it in the lab due to flammability issues. And then if possible, you would also do an IR and NMR. Of these, the IR for sure, you could see the double bond versus the OH group, so you could tell. The NMR, you would be able to see the different hybridizations and different chemical environments of the hydrogens. But that's all stuff you would do in lab. We can't really go over that stuff right now. And that will about do it for week 10 of your organic lab section. Pretty fairly simple lab, just E1 versus the SN1 we covered earlier. Just continuing on our paths, and in the coming weeks we'll probably do some SN2 and E2 reactions, as well as some qualitative analysis testing later on. Have a good week.